Transformers are everywhere, inside and outside of your home. They're in TV sets, sound systems, computers, and almost every electronic device. This thing is a very familiar transformer that is often used to provide lower voltages to electrical devices that cannot connect directly to the higher voltages of the wall. Also familiar are the transformers that look like trash cans high up on telephone poles. There's probably one near your school or neighborhood. These transformers are used to step down the voltage and correspondingly up the current to make it safer in the home. Understanding transformers involves knowing that currents can produce magnetic fields, and conversely, that changing magnetic fields can also generate currents. When I pass current through this coil, the compass will deflect. It's an electromagnet. Now we perform the reverse experiment. When I move this magnet through the coil, the galvanometer indicates that a current is flowing. Notice that when I hold the magnet still, no current is produced. The magnetic field must change in order to produce an electric field that motivates the charges. Note also the direction I move the magnet makes a difference. Since Michael Faraday was the first person to publish this discovery, it's usually known as Faraday's law. Now, the transformer puts both of these ideas together, but instead of using a bar magnet, it uses an electromagnet. When I turn on the power supply, it briefly produces a changing magnetic field in the first coil, and that produces a brief electric current in the second coil. Also, when I turn the power supply off, again there is a brief current, but in the other direction. This is the fundamental design of a transformer. Two coils that are connected magnetically but electrically separated constitute a transformer. The magnetic flux between the coils is greatly increased when a soft iron bar is added. This improves the efficiency of the transformer by strengthening the field and preventing it from diverging out and being wasted. Whoa, much better. The transformers found in home appliances usually look like this. Here are the coils, which are wound on top of one another, and this surrounding structure is soft iron shaped to guide the magnetic field lines back around and through the coils. Typically, a transformer is supplied with an alternating current, since if the magnetic field does not change, the transformer would not work. Incorrectly using DC for the input of a transformer, like say a battery, might even damage it. The number of turns on an ideal transformer is in proportion to the voltage across those turns. Here I have turns in an 8:1 ratio, and the voltage of 3 volts from my signal generator is stepped up by that same ratio. It should be 3 volts to 24 volts, but this is not an ideal transformer, and there are some losses, mostly due to flux leakage. We need transformers because it's more efficient to send electricity at higher voltages. This is the symbol for a transformer, but here it's connected in an unusual way. There's a light bulb in series with the primary coil, which is connected to the power source, but also another light bulb connected to the secondary coil, which is powering it also. Here's the same setup in real life. As you can see, both bulbs glow. Now, what do you think will happen if I remove the bulb in the primary circuit? No real surprise there. I cut the power to the whole thing, like opening a switch. The next question is, what do you think will happen if I remove the bulb in the secondary circuit but leave the bulb connected in the primary? Aha! Without the second bulb, there is an increase in impedance to the current flow. Impedance, Z, measured in ohms, is the ratio of the voltage drop across a device to the current that passes through it. This is very much like resistance, but it's a more general term that refers to all the elements of the circuit: inductor coils, capacitors, and resistors. We usually discuss transformers for stepping up and down voltages, but they should also be thought of as impedance matching devices. When the secondary circuit is open, there is no current to flow to oppose the changes in the primary circuit, and it experiences self-impedance. If you want to do this demonstration yourself, you must have an efficient transformer, and you should try to have the same wattage bulbs at their appropriate voltages in the primary and secondary circuit. For this purpose, we used an isolation transformer, that is, a transformer with a turn ratio of 1 to 1. It is convenient to alter a duplex outlet so that each outlet is in series with the other one. This can easily be done with an inexpensive duplex outlet that has had one of the copper connections between the two outlets cut. Using an extension cord with the insulation stripped away, connect to either screw of the cut side. And now we have our series outlet. Mount this in an outlet box for safety and clearly label it as a series outlet. It's not unsafe to mistake this for a regular outlet, but most items will probably not work in it. If you don't already own an isolation transformer, you can buy a small triad transformer for about $20. Its only shortcoming is it has a small power rating and should only be used with bulbs of less than 25 watts. If you have a high-quality step-down transformer like this 10-to-1 toroidal, then you can still do the demo, but you should work to ensure that your light bulbs have the same wattage. Toroidal transformers have excellent flux linkage, and so they tend to be more efficient. One more thing. Since transformers have to match impedances in order to work, it would make sense that you would have different transformer constructions for different frequencies. These are high-frequency transformers for television application. These are Balun transformers that are used to match the impedance of the 300 ohm flat TV lead to the 75 ohm impedance of the coaxial cable lead. If we look inside the transformer, we can actually see the windings. The transformer is toroidal, and the wire is wrapped around this ferrite core. Since it is used to match 300 ohms to 75 ohms, the coils have a different number of turns. Transformers are everywhere, matching impedances in multiple ways. A good lab might be to have your students try to figure out the turns ratio of a mystery transformer by measuring the voltages. Remind your students that twice as many turns will have twice the amount of flux through them, and therefore twice the voltage will be generated for the same change in magnetic field.